Okay. Hi, everyone. Welcome. Thank you for coming to this talk. I'm Julius, co-founder of the open source Prometheus monitoring system, and also the one person behind the company Promlabs. That's just myself. With Promlabs, I do trainings mostly these days. I also did some software in the past, but right now I'm just teaching companies and other people learn Prometheus. Today, I actually want to talk about a topic that I had almost no involvement in building in Prometheus, but that I was so excited about that when Thomas asked me, hey, do you want to come talk here? This is the best topic I could come up with. And so native histograms are a really new, cool, experimental histogram feature in Prometheus. I'm curious, who here is using histograms a lot in Prometheus? Okay, plenty of fans. And who has the situation where you're going like, oh my God, my Prometheus server is kind of dying because it's all getting too expensive because of the histograms? Okay, a few. So it's for those people. This talk is the target audience. So everyone else can leave now. No. Okay, but yeah, all the credit goes to mostly these three people and a couple more. Björn Rabenstein was the one who originally came up with the desire and then the ideas for how to build better histograms into Prometheus. Ganesh is helping out a lot these days, especially on the TSDB. Dieter Plating was there in the first hackathon where they really hashed out the ideas around this. But by now, many others are helping as well. So first, a quick recap around the classic histograms that have existed in Prometheus for many years already. What's good about them? What's maybe not that great? First of all, histograms in general are just a way to track the distribution of a set of values into a set of ranged buckets, so you have an idea of their distribution. For example, for request durations, how many slow requests do you have, how many fast ones, and so on. You can represent histograms normally, where every bucket bar just contains exactly the count for that range. Or the same histogram in a cumulative representation would be this, where every bucket also contains the counts from all the previous buckets. So you could also imagine this as every bucket actually starting at 0, which has the advantage that if you represent it cumulatively, for each bucket, then you only need to actually track the upper boundary. So for a second, let's go back to the Prometheus TSDB's data model, at least the way it was before native histograms. In the TSDB in Prometheus, we track metrics or time series. Every metric has a metric name and then a set of labels by which we split up that metric. So that's the time series identifier, and then there's just a stream of samples. Each sample has a timestamp and a value. But so far, the sample value has always only been a 64-bit floating point number. No matter what you put in there, it's always a 64-bit float. So how can we even, how were basically those old histograms retrofitted onto this dumb data model? The idea here is we went with a cumulative histogram because then we could easily expose a single time series for every bucket that gives you the current count for each of that buckets. And we only need one label on that bucket, namely the upper bound, because it's a cumulative histogram. You had to still manually configure in your instrumentation how many buckets you wanted to have and what their specific upper bounds were. So that was a little bit cumbersome. This is how they were serialized. You have these different buckets. This LE label is the string-encoded upper bound. LE stands for less than or equal. So this bucket contains 20 requests that have finished in less than or equals 25 milliseconds. That's what it means. And so for each bucket, there was one time series. And then we also exposed the total sum of observations. So for example, the total request handling duration and the total count of observations. For example, the total count of requests. So histograms already served people pretty well over the years. They do a lot of things great already. For example, they're very efficient at tracking things in a high frequency. Like, let's say you're getting tens of thousands of requests per second. Then tracking all those into histograms still works pretty well. There's just a bunch of counter increments happening under the hood. They allowed you to calculate stuff like percentages, ratios, averages. For example, if you have a bucket boundary at exactly 100 milliseconds, then it's very easy to calculate from a histogram what ratio of all my requests finished within 100 milliseconds. You could also calculate percentiles or quantiles from histograms. That's the histogram quantile function. Like everyone who uses histograms in Prometheus uses that all the time. And you were able to partition those classic histograms by additional dimensions. Let's say you want to split up the histogram by a path, by a status code, by a method label or so. You could do that, but it comes at an extra cost because then all your buckets are multiplied with that additional dimensionality. But then when you had that dimensional partitioning, you were able to aggregate again over all those subdimensions and get to something like, hey, give me just the per path latency or the total systems latency. So lots of good things, but lots of people also suffering because we need to create one time series for every bucket. That means if you want to have a high resolution histogram, you also need to create many, many, many time series. And the number of time series in a Prometheus server is usually the scaling bottleneck, where like the memory blows up and eventually your server is not happy. And you also had to choose these buckets statically and relatively manually in your configuration in the client library where you track these histograms in order to work well with these histograms later, to be able to aggregate histograms from two different paths or two different service instances, for example. They also had to be relatively static and the same between those subdimensions. So that means like if one path has a totally different latency behavior from another path, you still had to choose the same bucketing scheme, even though they were not really ideal in both cases. So in practice, like there's just been a huge trade-off between the cost and what you get out of these histograms in terms of resolution, and lots of overloaded Prometheus servers. So can we improve that while keeping all the benefits? And of course, yes, otherwise I wouldn't be here today. The answer is native histograms. The first question here was, okay, this one series per bucket is kind of ludicrous. Can we maybe just put an entire histogram in a single sample value in Prometheus? That's the first thing that was done. So now the TSDB data model in a single sample value supports that. It can either be a 64-bit float or an entire histogram, including the sum and counts and not just the buckets. But can we also wait. Oh, that's interesting. Let me just check one thing. I think 2 slides went the wrong way around. So this should come first. Can we also have better histogram structures than before? Where we don't have to specify all the buckets up front, and maybe it can be sparse buckets, so you can have very fine-grained buckets, but you only need to track the buckets that you actually have requests for. And that already exists in some other systems, but it was a little bit harder to make work with Prometheus's computational data model and the pull model. But the answer is yes. So the actual structure of those histograms looks like this. I'm trying to explain all of it in this one slide. First of all, exponential buckets. That means there's always a bucket with an upper boundary of 1, and everything else kind of revolves around it. And the only thing you need to provide is a bucket factor. That's that factor there. Could be 1.1, 1.2 or so. And then that defines all possible buckets, which is like theoretically an infinite amount, but practically somewhat limited. And the good thing is that you don't need to actually track all buckets. We only track the buckets that actually have requests. The empty buckets are not tracked. And since it's exponential, we don't want an infinite number of buckets towards 0. We'll just be getting like infinitely tiny at some point. So there's a 0 bucket where you just provide some, in practice, much smaller upper bound saying like, hey, at 0.00 something 1, don't create any more tinier buckets. We just count everything into the 0 bucket. Yeah, what else? It's no longer a cumulative histogram, meaning that each bar really just contains its own requests, so to say, because it's sparse, and that wouldn't work well with the sparseness. Other than that, every bar is still conceptually a counter. All these bars start at 0 when your process starts up, and then they just gradually increase as requests trickle in, and then later on we do rates over that and stuff like that. In reality, it's not, the bucket boundaries are not the ones that I'm showing here. I'm just showing like powers of 10, so it's easier to see. In reality, I'll show you what they are. So yeah, that was that slide where two things were reversed in my slide deck. Sparse bucket usage. So there's a question around that, right? In the ideal case, you have some islands where requests are really happening in your latency distribution, and that's where your buckets actually appear. But over time, you could run into this issue where some requests even happen somewhere in between, and you end up with a lot of buckets again, but only like 1 or 2 requests each, but you still have to track them. So, over time, your histograms will suddenly become more expensive again. So can we do something against that? In practice, yes. We can just reset the entire histogram once in a while, because every histogram bar is conceptually a counter. Even if it's no longer a single time series, it's still a counter. And before you do anything with a counter, you need to take a rate of it anyway, or an increase or irate. And any counter can anyway reset at any time. Like when your service instance restarts, it will need to start at 0 again. And all those functions, rate, irate, increase, they deal fine with occasional resets. As long as those resets don't happen with a frequency that comes close to the scrape frequency. So yeah, that works pretty well to kind of garbage collect that entropy. And a really cool feature of this of these exponential buckets is resolution downgrades and aggregatability. When you specify this bucket factor of like 1.1 or 1.2, that's not the actual factor that's being used. The actual factor, so that's just an upper bound, and it's being matched to one of these actual factors that can be used. They're all 2 to the power of 2 to the power of minus n. And that scheme means that like all these different bucket schemas, like these different factors, lead to multiples of 2 in the bucket widths between those different bucket schemas. So in the end, with the new histograms, you can take any 2 histograms from anywhere and somehow aggregate them, because you can just take a high-resolution histogram, and if you want to convert it into one that's like half the resolution, then you just combine 2 buckets, you add the 2 counts together, and then you have the lower resolution histogram. So you can downgrade the resolution in case it becomes too costly, but you can also do it if you want to add it to some other histogram that has a lower resolution. So many advantages here. We need to track and index way fewer time series in the TSDB. The actual encoding between subsequent buckets within a single sample value is now also more efficient. There's some delta encoding going on. Again, unused buckets are free because it's a sparse histogram. Thus, you can afford a much higher resolution. You can aggregate all different schemas together. And the only thing you really need to configure is the bucket factor. How do you enable this in a Prometheus server? Currently, hazard warning, it's still experimental, but you can turn on the content negotiation for it and the ingestion using a feature flag, native histograms it's called. And that will cause Prometheus to send out an accept header that includes a new protobuf-based scrape format. Currently, the new native histograms are only supported in the protobuf format. There's some text format support being worked on that will come at some point. But protobuf is more efficient for these currently, like all these many buckets that get transferred. And that is also currently only implemented properly in the Go client library. So if you want to try it out, use the Go client library. In instrumentation, let's have a look first at classic histograms. You needed to specify all the exact buckets and their upper bounds. Even if you auto-generated them, they were still fairly static. Whereas with the native histograms, it changes to this. You only specify a factor. And then all the right buckets start appearing in the right places, and the ones you don't need, they don't even get exposed. There's some optional settings as well to prevent the creation of too many buckets, and around when to garbage collect and reset buckets and so on. For details of those, go to this link down here. Let's have a look at native histograms in PromQL. Like, what do these look like in actual queries? First of all, cool thing, we don't need the underscore bucket in the query anymore to get the actual histogram buckets. It's just the base name now, and it contains an entire histogram now. Currently, it looks a little bit obtuse. Right? It's still early, it's still experimental, but you can see the count, you can see the sum, and then you have the different bucket ranges and the current counts here. And yeah, so that's an entire histogram in a single sample, whereas previously you would have only seen a single float value there. I'm working on making this a little bit prettier like this, but I don't know exactly what it should look like yet. Yeah, and then you can do stuff with it. So again, all these counts, values, bucket counters, they're all counters, so you probably want to take a rate over it first. And the rate function just works on histogram samples as well. So it just takes the rate of all the individual counters and returns you a derived histogram where every field has been rated. So for example, this would now be like this count field. Rated now means, hey, this is the actual request rate over a 5 minutes window. Then we can aggregate using the sum aggregator as before. As with a normal histogram, we preserve some labels and throw away others. And we can calculate quantiles, even simpler as before. We just use a very similar structure, histogram quantile, wrapping a sum aggregator, wrapping a rate. But we don't need to explicitly preserve that LE, that less than or equal label in the aggregation, because that doesn't exist anymore anyway. It's all part of the structure of the histogram itself. Here's a comparison. Classic histograms and the native ones, calculating a 90th percentile latency from them looks pretty similar. I would guess that probably the results are a little bit better on the right-hand side. And you can see the queries look almost the same, except there's no LE label, and I don't have the underscore bucket with the native histograms. There's some new functions as well. For example, to calculate the fraction of requests that have finished within given bounds. For example, all the requests that have finished between 0 and 50 milliseconds. And if I do not happen to have upper boundaries of buckets at exactly those specified times, it will just interpolate within a bucket. Then we do have accessor functions for getting the sum or the count fields out of that histogram function in case you need them, right? If you just want the request rate. And you also can use binary operators already to a large degree. For example, using a plus to add two different histograms together works. Some real-world results, because you might be curious, like how good is this actually in reality? I don't have access to a large production use case of this yet, but Björn Rabenstein gave a really awesome talk at Observability Day Europe, where he ran this in production at Grafana Labs, and he compared classic with native histograms. Watch that talk, it's really awesome, but the very rough takeaway is he got 10 times the resolution in practice for half the price. So if you have any really big histogram woes about cost and so on, it's really awesome. Query times didn't change much, roughly the same. Some things take a tad longer by their nature. For example, if you're only interested in the count field, it's a little bit cheaper with the old model because it's just a single time series that's already there. With the new one, you have to kind of decode the entire histogram first and get the count out of there. And he also noticed that the bucket entropy and the required resets were reasonable. That means the histogram didn't have to be reset like every couple of seconds. He also did a comparison of a Grafana heat map. So left side classic, right side the native ones again, and you can just see way more resolution, especially in the interesting bands in the new one. All right, so keep in mind, all of this is still experimental, but please try it out. give feedback. Now is still the time, although it's getting more and more stable by the day. And yeah, if you want to learn more about native histograms, there's a whole bunch of talks, both by Björn and Ganesh on YouTube. And finally, shameless plug. This is just my company. So, if you want to learn more about Prometheus in general, I just started a YouTube channel in December, I think it was, where I do like these clickbaity videos where you can learn stuff around Prometheus. And my self-paced training courses, I have a special KCD offer with a coupon code KCDZRH 2023, and the first 20 people who use it get 30% off. All right, thank you very much. Any questions?
Anybody? Questions?
Yeah, maybe. Can you hear me? The metric, the factor you showed, I wonder why the number was 2 power 2 minus n. What is the logic behind the default one?
Okay, yeah, so basically you don't only want to have powers of 2 in terms of bucket schemas, but you want to make sure that each next schema, the buckets are twice the width of the previous schema, so that's what that ensures. So it's not just, hey, we allow any power of 2 schema, but only the ones that are twice the width of each other. And that's what this formula basically guarantees you. And the current actual schemas that are supported are from 8 to -4 for the n, because that covers pretty much the whole realistic range of factors you might want that are possible in that schema. From like really, really tiny factors to humongous ones.
Thanks.
How is the adoption going on for the services and tools to use it, considering it's still experimental?
The adoption is still very early, I would say, because it's still experimental, because people are still even trying out whether everything works as intended, and even for some of these promql functions I should have mentioned, these accessors. Histogram count, histogram sum, those might disappear again. They might actually become syntactic features of the language. We don't know that yet. But yeah, I think many people are still waiting to see that nothing changes anymore. And so like production adoption isn't large yet, as far as I understand it. But some people are starting to use it, probably mostly some people at Grafana Labs, where most of the implementers are. And yeah, maybe some others, but yeah, not too sure. I would guess it's pretty low at the moment still.
Hey, quick question on the reset of the histograms. Did I understand correctly that you have to specify the maximum there, or what is the logic when you're somehow choosing when to reset? Do you have to specify the time of resets, or?
This slide here, the different options. So why we do resets, you understand, right? Yeah, yeah. Basically, yeah, there's a whole logic explained in this link, but basically, there's some strategies you can do when you get too many buckets. Either you can decrease the resolution, like by just going to double width buckets. That's one possibility. But before the client library does that, it tries to increase the 0 bucket threshold to also get rid of some buckets like that. And then there's also a time-based option for like, hey, we just reset everything. And these factors play together in different conditional ways that are described in a huge-ass comment in the link below.
Oh, so just specifying a max number of buckets should work, right?
Yeah, as far as I know, like if you specify just like, hey, my max number of buckets can be this, then you will never go above that. And then the client library will try all these different strategies to try to stay under that.
Okay, thanks.
Mm-hmm. Any other questions? Wonderful. Thank you.